Okay. Yeah. So PET scans, positron emission topography. That's basically for cancer detection. CT scans are scans that can show certain areas of your head or other parts of your body that are damaged or diseased. Targeted alpha therapy, same concept. I don't know all the intricacies of these things. I just generally understand the concept. Radiation therapy, that's when you blast radiation at cancerous tumors to kill them. Cobalt-60, let's write that down. CO-60 is a good one for that. Radioactive tracers, you're using a tracer for the PET scan where they inject this solution in your bloodstream with a tracer attached to glucose. It's tagged, they say, and I think I talked about this Friday. Tumors, I think it was period 6 I talked about it, I don't know, but what do tumors do? Why is cancer so bad? Rapid cell growth, right? Like uncontrollable cell growth. And cells, when they do that, need energy. Well, where's the prime source of energy for your body? It's glucose, sugars. So the glucose kind of accumulates in those areas in your body. Like if I had a tumor over here, there would be a lot of glucose being used over here. These tracers are put or tagged to that glucose, and it gives off radiation. So when you take the PET scan, that area is going to be very bright. They call it bright spots because they can see that glucose giving off radiation. There's a lot of it over here, and nowhere else, because that's where the cancer is. So that's relatively important knowledge. All right, I'm sure you know somebody with cancer, or you will. But anyways, which is sad, but you probably will at some point in your life. And that's a big thing with detection. Let's see. Just straight up X-rays, right? X-rays of your face, your bones, whatever. For your dentist, if you break a bone or something, obviously that's radiation, but that's easy stuff. There's another one called boron neutron capture therapy. I'm not going to list every single thing I have here. Let's see here. Yeah, I have a whole list of things that we can talk about, but we don't really need to talk about all of these. On the regions, there's 5 isotopes they may specifically ask about. This is one of them. Cobalt-60. Which of the following is the use for cobalt-60? Radiation therapy is the answer. Okay, that's what cobalt-60 does. It gives off gamma, and the gamma rays are shot at tumors to try and shrink them or kill them, and that's one. That's one of the isotopes we need to know. There's 4 more. Iodine-131 is another one. It's used to detect thyroid disorders or thyroid issues. If it's too big, too small. The way I tell kids to try and remember it is just exaggerate the word thyroid. Iodine, thyroid. Okay. So remember, iodine-131 is a really common isotope on the regions. Cobalt-60, iodine-131, carbon-14. This is for dating organic material, meaning figure out how old it is. That's carbon dating. Carbon-14 is the isotope we use for that. U-238 is for dating rocks, essentially. Geological things. Geological formations. How old some rocks are. So if you want to know how old the Earth is, you can do it using geological dating with uranium-238. Because uranium-238's been here since the beginning of Earth's formation. So based on the half-life, we can figure it out. The half-life of uranium-238 is pretty close to the age of the Earth. How old is the Earth?
Oh.
Look at the half-life on table N. What's the half-life of U-238? 4.5 times 10 to the 9th. How many years is that? In like normal words. 4 billion. 9 zeros would be billion, right? So 4.5 billion years old. What am I forgetting here? Oh, technetium 99. TC99. Now, I always wrote in my notes detect brain tumors, but I just looked at this sheet, which I've had for years. Used in an image used to image the skeleton, heart muscle, but also for the brain, thyroid, lungs, liver, spleen, kidney, gallbladder, bone marrow, salivary and lacrimal glands. Lacrim? I have no idea what those are. Heart blood pool, infection, and numerous specialized medical studies. So technetium 99 apparently is used for a lot. I'm just going to write down what I've seen on the Regents. Brain disorders, or brain disease. That's not a very good way to write that. Sorry, it's Monday. I haven't made any mistakes yet, though. So it's a good day so far. Basically, they can use that isotope to kind of detect brain issues with your brain. This one and this one are really common on the Regents. This one makes sense because it's more of a, people have heard of that, even if you've never taken chemistry. This one I'm not sure why it's as common on the Regents, but thyroid disorders are actually extremely common, real common, that people have to take synthetic drugs because the thyroid doesn't work properly. It's extremely common. I know like 10 people that have to take medication. Maybe not 10, maybe like 7. But it's pretty common. All right. And that's really frustrating for them because, I don't know, you guys know what thyroid does? It essentially regulates your hormone production for the entire body. I know the pituitary gland does that too, but your thyroid's kind of the boss there. So if that doesn't work very well, you just feel like crap. And people that have overactive thyroids, they're like they sweat all the time, their heart rate's super fast, they eat massive amounts of food, they don't sleep very well. It's almost like you're like super like anxious and hyper all the time. And then people that have thyroids that don't work well enough, never hungry, but they have weight gain, they're tired all the time. It's like the opposite. And either way, you don't want to live that way, right? You want to be in the middle. So, anyways, I guess maybe that's why it's part of the test, because that's kind of a big thing. All right. I think that's it. Just want to make sure I'm not forgetting something. I wrote a note to make sure I didn't forget. All right, so we'll watch the video on carbon dating. Does anyone know how that works? Did I talk to you about this before?
It's mostly a joke.
Oh, we're a half you, Ben. Yeah. That's so stupid. Funny. I told you all my cheesy jokes last Friday, didn't I?
Yeah, it was on Thursday.
That was Thursday. Come on, the Adam's walking down the street. That's hilarious. Are you sure? Yeah, I'm positive. Come on, it's fine. Are you no charge? All right. Here we go. Oh, there is one more thing. Aha, good thing. We have this open. All right. After we watch the video on carbon dating, there is one more thing we got to talk about with the four types of radiation. What are the 4 types again? What can be emitted from the nucleus? Gamma, beta, positron, alpha. Good. What's the charge on gamma? Neutral. Good. What about alpha? Positive. Positron. Beta. Good. So when we get to that, it'll be easy. All right, here we go. How carbon dating works, and then we will take notes on one more thing, and then we'll start bonding. Zeke, you want to help me out? Please. All right. Thanks, Reagan.
I could do it for you.
No, I mean, I can do it. I just don't feel like doing it. Okay. All right. So, this is cool. I think it's good to learn this.
how do we know how old something is? For people, we'd ask to see their birth certificate. For trees, we count the rings. But how do we know how old a fossil is? Fossils have their own internal clock. Scientists can read it by looking at the ratio of two different types of carbon atoms. Of course, every living thing is made of carbon. Plants grab carbon dioxide from the atmosphere and use it to form complex organic molecules. Animals get their carbon by eating these plants. But there's more than one form of carbon. Most carbon atoms have 6 protons and 6 neutrons. We call this carbon-12. High up in the atmosphere, sometimes cosmic rays hit nitrogen atoms. This creates carbon with 6 protons and 8 neutrons. We call this carbon-14. Carbon-12 and carbon-14 behave alike, but carbon-14 has one unique and important attribute. It's unstable. So once an animal dies, the carbon-14 in its body will start to go away. Every 5,730 years on average, about half of the carbon-14 atoms will decay into nitrogen. This is its half-life. After one half-life, the animal will have about half the amount of carbon-14 it started with. After another half-life, it will have about a quarter. And after another half-life, it will have about an eighth. By contrast, the amount of carbon-12 it has in its body will stay the same. By measuring the ratio of carbon-14 to carbon-12, we can measure how many thousands of years have passed since the animal died.
So that, he's going to talk a little bit more, but that's basically how it works. So when you're alive and breathing, you're breathing in carbon dioxide, which has carbon-14. You're eating plants, you're eating animals. People eat one of those two things. Everybody does. Or both. So when you're living, essentially your ratio of carbon-12, carbon-14 is the same. But when you die, your carbon-14 will deplete, like he's explaining. It's radioactive decay. It breaks down, gives off beta. So right now, all right, you're alive, and then you die, and then after 5,715 years, you have half as much carbon-14. So based on the ratio of fossils or whatever's found, they can analyze it and say, okay, here's how much carbon-14 is in this sample, this fossil. Here's how much carbon-12. And again, based on the ratio, they can work backwards and say, all right, this thing's about 20,000 years old. Now, things that are like extremely old, millions of years old, they could be off by, let's say something's roughly 200 million years old. They could be off by 1 million years. Now, to us, that sounds crazy. But if it's that old, that's still a pretty good estimate. You know, if it's 200 or 201 million, it's so old and so long ago, that's not bad, right? So it you know, in between here, it's kind of an estimate, educated guess, but that's how it works. Does that make a little sense? Sort of? At least it should make sense. You have carbon-12, which stays constant, and the other one decays. Based on that ratio, using the half-life, they can figure out the age. That's the short way to explain it again.
Carbon dating works for fossils up to about 60,000 years old. For older fossils, scientists use unstable elements that have much longer half-lives. For Scientific American's Instant Egghead, I'm Michael Moore.
I think they use it for longer than 60, but 60,000. But the point is, that's what he was saying there. What I was saying is they have to kind of guess because it's so old. All right, so another video. I want you to draw something in your notes here. Not that. Okay. I want you to draw. Okay. Oh, what? Did I freeze you guys? Yeah, but I did not. Oh, I see. I'm on my. Stop. There we go. Sorry. So, in your notes, I want you to draw this. Draw a box, and then over on the side here, I want I forget which ones they're going to do here. Okay, positive and a negative. I want you to draw one arrow going straight through, one arrow bending up. One arrow bending down and then another one bending down, but not quite as far. All right, and we have 1, 2, 3, 4. This is the last thing with nuclear. Okay. So this box here is shooting out different forms of radiation. Now, if you bring radiation in the presence of an electric field or magnetic field, so let's say these are two plates and electricity is passing from one to the other. When radiation comes in contact with the electric field, if it's strong enough, it will deflect or repel radiation based on charge. So we said gamma has no charge, alpha has a positive, positron positive, and beta is negative. So if this is a positive plate, this is a negative plate, try and think what makes sense as far as which type of radiation would go straight through, not affected by either one, which two of them will be kind of attracted to the negative, and which one will be attracted to the positive. They're going to explain it. You probably already have a good idea, I hope, but this is the last thing I wanted to show. I remembered, thankfully.
A source of radioactivity is passed through a hole to form a beam. The beam is directed at a fluorescent screen, which is illuminated when it is struck. In the absence of an electric field, all the radioactivity beam strikes the target at a single point. When an electric field is applied, the initial beam is separated into 3 components. One of these is deflected upward by the electric field, indicating that it is negatively charged. These radioactive emissions are called beta rays. A part of the beam is deflected downward, indicating that these particles are positively charged. These radioactive emissions are called alpha rays. Notice that the alpha particles are deflected less than the...
Okay, so number 1 is beta. Make sure we write that. Number 3 is alpha, not number 4. Number 3 is alpha. I know our notes have 4, they only have 3. They don't talk about positron. What's the one in the middle? Gamma. Gamma isn't deflected. She's going to get to that. But number 2 is gamma. Number 4 is positron. Does it make sense to you guys that the alpha and positron being positive are attracted to the negative? Everybody with me? Yes? And it makes sense the negative is attracted to the positive? And then it makes sense gamma is not affected. Now the word the Regents is going to use is deflected. So eyes up here. It's going to say deflected towards the positive, deflected towards the negative. I don't like that. In my mind, I'm like deflecting things away from me. They don't use that. They use it the other way around. They say deflected towards. That sounds like an oxymoron or something. It doesn't make sense, but just be prepared for that. And the last thing with this, and she's about to explain, but I'm going to cut her off. Why does the beta travel further up than the alpha travels down? What's lighter? Very good. Yes. If I have a golf ball or a shot put, I can't throw the shot put anywhere near as far as I can throw a golf ball. Okay? Even if I try and throw a shot put like a golf ball, I'll probably rip my shoulder apart. Okay? You got to do that thing. I don't know how to do that. But the point is, I can chuck a golf ball pretty far, but a bowling ball, another analogy, I can't throw that as far. It's the same thing. The beta is lighter, so it deflects further. Alpha is heavier, mass of 4 over 2 He. So that's not going to be able to get pushed as far because it's bigger. Does that make some sense? All right. Perfect time. Look at that. All done. And no homework. Happy Monday. And we have lab today? What a beautiful day. It's sunny. Birds are chirping. It's freezing cold.
Check my watch. It feels like -3.
Chem lab. What you reading? Lights, please. Vanessa, quick. Thanks.